Yes, I'm Alison Strachan. I'm a consultant at Fraser Nash, who's one of the team working on this project. And I'm going to take you through the presentation today, and then we have other members of our team from the different partners available to answer some of your questions at the end. So if we could have the next slide, please. Okay, so yeah, our partners on this are National Grid, who is the project lead, National Grid Electricity Transmission. And we have VIA, who are developers of the technology that we are going to be talking about in this project. We have the University of Strathclyde and the University of Manchester, who have been doing some of the analysis work for us, and Fraser Nash, who I'm part of, who've been doing some of the road mapping and the techno-economic analysis. If you could go to the next slide, please. So this afternoon, I'm going to give you an overview of our project, tell you what a Scohl system is and what possible use cases there could be for it, what the key findings we have from our discovery phase, so split into three categories: technical challenges and opportunities, a bit about the costs and benefits, and then some engagement with other interested stakeholders that we undertook in the part of the project. We'll then talk about the roadmap, so the roadmap to get this technology to business as usual, and what we have planned for the alpha phase, and then we'll have some questions. So yeah, next slide, please. Okay, so project overview. So as Beth said in her introduction, obviously there's a huge ambition if we're going to achieve net zero, and that's going to mean a significant increase in electricity demand for various different industrial sectors and domestic sectors too. The usual way, if you're going to increase the capacity of a circuit, one of the usual ways is to either add an extra circuit, but if you already have a lot of circuit capacity, you can increase the voltage. So if you have a 275 kilovolt circuit, you can increase the power capability on that circuit by raising it up to a higher voltage. Unfortunately, that can be a bit of a problematic thing to do, because as you're going to higher voltages, you have potentially long consenting times for these projects and long lead times, because obviously as you're going up to higher voltage, you have a higher visual impact. The towers are bigger. There's bigger width of corridor required for the technology, and there's also the construction can be more complex and require a bit more specialist equipment. So therefore we propose a solution to that would be Scohl, so superconducting overhead line technology. These could be used to operate existing line routes to achieve up to 5 times higher power capacity, and also reduce or remove the need to use conventional 400 kV, so reducing the cost and footprint of the infrastructure like I just described there. Next slide, please. So what is a Scohl system? Okay, so superconductors, the SC, are materials that have almost no electrical resistance at low temperatures. And what we're looking at in this project is high temperature superconductors, which are still pretty cold, but they operate at the temperature of liquid nitrogen, which is around minus 196 degrees Celsius. And liquid nitrogen is a common industrial coolant. So earlier superconductors were, cooled by other gases which were very close to absolute zero and very difficult to bring out into the field. Whereas with liquid nitrogen, it's a very common industrial coolant, so you can use it in more applications. So our project partners VIA have developed a novel open loop cooling system that allows high temperature superconductors to be deployed as overhead line. And the reason that this works is that cooling with liquid nitrogen in a closed loop system has significant weight issues associated with it. And that kind of restricted high temperature superconductors to cables, so underground cables only. But this novel technology, which there's a paper there which describes the science, which is really, really interesting if you want to go and read that, has this open loop cooling system which removes or reduces those issues. And the system that they've developed comprises HTS tape, which is the conductor, in an insulated jacket, which provides the cooling, And then there are pole top units along the line to manage the temperatures and pressures of the liquid nitrogen. And that picture there is one of the pole top units that they've deployed and they are testing at the moment. What it is, it's a transformer can size, usually used, those sort of transformers are usually used at distribution in the States. So it's relatively small. It fits, as you can see, on a pole, a distribution pole there. You could do the next slide, please. So what are the possible use cases for this technology? Okay, so we came up with a number of different scenarios, and we reduced them to, in the discovery phase, to the three most useful cases, I suppose, are the most prominent cases. So the first case is, as we've probably already discussed, upgrading 275 kilovolt lines to 400 kV. So because, as I said, the power density can be increased at 275 using superconducting lines, you're basically increasing the power capacity without uprating the voltage and without making the infrastructure a lot bigger. So that's a very big advantage that we'll talk about a bit later on. The second use case that we came up with, there's a potential to use future overhead line to underground cable superconducting network. So some of you may be aware that we've also been working on another project called Scadent, which deals with underground superconducting cables. So potentially what we see here is a linkage between the overhead line and the underground cable, so that, for example, it could be used in areas of outstanding natural beauty, where we could bring a superconducting overhead line up to the boundary, underground the cable using HTS through the sensitive area, and then go back up to an overhead line after that. And then the third case is again very relevant to the net zero ambitions. It's a rapid deployment of new network infrastructure. So as we talked about earlier, for operating lines, you get much longer consenting periods because of the various regulatory issues around those. If you are building new lines with 275 kV as opposed to 400 kV, you can potentially get those connections made quicker and therefore bring online more renewable generation at an earlier stage, or supply additional demand at an earlier stage than you would be able to with a conventional solution. Next slide, please. Okay, so from our discovery phase, the key findings, the first one I'm going to talk about is technical opportunity. So there is a huge opportunity for this technology. As we've said, significant amount of network needs capacity upgrade to deal with the increasing demand and the renewable generation that's coming on stream. And that there's a number of projects and funding initiatives are going on. For example, ASTI at the moment that recognise that, and this would be another one to add into the sort of various suite of options that are being talked about. There is over 4,500 kilometres of overhead line in England and Wales, which makes up 95% of transmission circuits. So this has a big potential to be used on the network. And that system also comprises around 22,000 transmission towers and around 340 substations. So you can see it's a pretty big job to upgrade the network. So if we can come up with good solutions to do that, that's also good. Now, reconductoring circuit, so basically putting in a higher capacity line, is a fairly common practice. So it's not an unknown thing that you could replace one conventional conductor with, for example, a superconducting line. And Scohl, like we say, is another technology that could be used to add to that sort of the suite of options that are available to National Grid for these upgrades. And one of the things that we found in our research for the discovery phase was that many of the towers that are on the network have existing CAD structural models. that we could use or modify so that we could understand the structural issues posed by the different technology that is Scohl. So effectively, we're not starting from a blank sheet of paper there. We've already got some models that we could reuse in order to test out some of the challenges that we face with the Scohl technology. Next slide, please. Okay, so technical challenges and issues. There are several different designs of transmission tower on the grid. There's a couple of examples just there on the slide. And each tower is going to have specific structural issues related to its site and also its application. So some towers are suspension, some towers are in tension, and some are obviously terminations where when you get to the substation. So those are there's a lot of different structural issues that we would have to examine if we were going to roll out this technology. And if we wanted to retrofit to existing towers, we need to understand exactly the structural issues that are related to that. Now, 275 kV towers, which is what we're looking at for this project, are generally about 300 meters apart. And the current development of Scohl is focused on lower voltage systems for about a 75 meter span. And the first commercial project there is expected in early 2027. Now, being involved in this project does allow potentially an accelerated development of higher voltage Scohl systems. But obviously we have to take into account that if you are developing a conductor for a longer span, it needs to be thicker and heavier just to maintain the structural integrity. So that's the kind of issue that we would need to consider further in the alpha phase. And another thing that we found is obviously this is a new technology and there's a lot of gaps in the standards, both electrical and structural, relating to superconducting cables, superconducting wires, sorry, and how they would be integrated into the network, how they would be tested, all these different things. So that's another key area that we'll have to look at in the later stages of the project. Next slide, please. Onto the costs and benefits. So we did a generic cost benefit analysis of a Scohl system against a 400 conventional overhead line, which would achieve the same power flow but in a smaller footprint. What you can see from that graph is the Scohl cost is higher, but achieving cost parity is thought to be possible because, first of all, there'll be cost reductions as the technology develops. We're obviously looking at a technology that's being moved forward very quickly through its development phase at the moment, and as we develop that, costs will fall. And also, lower voltage deployment will lead to lower substation costs, smaller towers, and the potential to reuse infrastructure like towers rather than building new ones. These haven't been looked at because they're very very case and location specific. So that's something that we will do in the alpha phase. We'll look at a specific case and do a more detailed cost benefit analysis to show the cost savings or cost parity that can be achieved with superconductors. Next slide, please. Okay, and another thing that we did in Discovery was we engaged with a number of other stakeholders, which we found very valuable in scoping out the problem and finding some items of specific interest and getting some technical details that we in the project team didn't have enough expert knowledge on. So we engaged with a couple of grid customer organisations, and we're looking to include a bit more perspective from them in the alpha phase. We spoke to Scottish Power Renewables, who are a generator, significant renewable generator, and Microsoft, who are a large consumer of power and particularly interested in how they could get fast connections for data centers, which obviously are big power consumers in a small space. And we had some discussions with additional experts for some items that we needed to know a bit more detail about. So we spoke to Balfour Beatty, who are an installer of HV lines. So we wanted to understand the differences between how you would install a superconducting conductor versus our conventional conductor, and we got some very good insights from them. And also Allied Insulators, who design insulators, as is in the name. So we needed to get some information on the structural and electrical properties of insulators. So we've spoken to them about that. Next slide, please. Yeah, so this one is sort of just outlining the roadmap that we see for the progress to business as usual for this technology. We've obviously already done the discovery phase. In the alpha phase, we see, as I've described, developing a use case, doing a detailed cost and benefit analysis on that, and some detailed modelling of the electrical and structural parameters that we talked about. And also on the technology side, partners moving towards progressing the development of the technology at a higher voltage. And then we have plans to go through the beta and the beta phase and future phases, which we can maybe talk about in the questions, because I've gone over my time. So next slide, please. Yeah, and the alpha phase, really, we just need to fully understand the significant issues and challenges, technical, regulatory and commercial, how those interact. We're proposing 4 work packages, 2 to deal with technical and standard issues, 1 electrical, 1 structural, and 2 to deal with the wider commercial issues and to draw together the strands from the first 2. So that's our plan for alpha. And next slide, please. I think that's me finished. Yeah, thank you. Hand over back to you, Beth, for the questions.
Brilliant. Thank you, Alison. Great presentation. We do have a couple of questions coming in, or maybe more, in the Q&A, which is good. So I'm going to start with those. So first question is from an anonymous attendee. How much deployment of this tech is estimated to be deployed in the medium term? And is there enough of a market size to drive a steep learning curve?
Okay, that's a good question. I can maybe hand over to Jessica for that one to talk about the development that they've been doing, and then we can maybe pick up with Sean about the GB perspective, perhaps?
Yes, that sounds good. Thank you. Ironically, the other industries are actually helping us bring down the cost. So the largest component cost of our overhead lines are the HTS tape, and the fusion industry is having significant investment to try to develop their technology. That has in turn prompted increased manufacturing. Most of the HTS so far has been research driven or demonstration project driven. So we see a steep decline in that. And then in addition, this problem that we're addressing is really a global problem. And so the ability to drive volumes through not just the UK, but other locations around the world, I think can help us give confidence that the cost will come down. Thank you.
Okay, thank you very much.
Sean, I don't know if you want to maybe make a comment just on the potential for this in GB. And we've talked a bit about it in the slides, but whether there's anything you'd like to add to that.
Yeah, thanks, Alison. No, I mean, at the minute, you know, in order to deploy it onto the GB transmission system, it would have to be a viable option at those transmission levels, which is what this project is all about. But thinking about how much capacity we need to increase on the network to facilitate net zero, there'll be plenty of opportunity 2030 and beyond. So it's really important, vital that we explore all those options that allow us to expand the network during the 2030s and beyond.
Thanks, Sean. Okay, next question is more of a comment around when's the best point to upgrade the HV lines? So Rob Walden says, presumably because of the cost of replacement, it only makes sense to upgrade HV lines when they're at the end of their life, unless, of course, there's a reason to increase capacity. So it's more of a sort of open-ended comment. I don't know if you have any insights on that.
Yeah, I mean, I could suppose approach it from the aspect of we would upgrade or replace conductors under 2 scenarios. One is when there's a load-related driver that requires us to upgrade the line to increase capacity of an existing line, and the other one is the end of life of the existing asset. Under those circumstances, we ordinarily would only upgrade. We wouldn't upgrade, we would replace like for like, unless there is a requirement and a business case that means we'd need to upgrade it for future capacity. But that would only be in agreement with Ofgem and consumers.
Great, thank you, Sean. There's another question from an anonymous attendee. Is the challenge that the suppliers are not able to find alternate gases or mixtures that meet the safety insulation character? Oh no, sorry, that was from the previous project. Excuse me.
Hi Beth, yeah, I think that was a lagging question from the last session.
Oh, I've done a lot of these show and tells. We get a bit of overlap. Apologies on that one. Have you assessed if there are any issues relating to the performance of this technology under fault conditions?
I'm going to hand over to Wager for that one. If Wager's available, sorry.
Oh yes, so I think that performances will be in the alpha phase. We identified it's important to study the protection schemes for both steady state and the transient state. So because of short duration of discovery phase, we managed to get steady state characteristic, but for the transient characteristic, the alpha phase will give us enough time for us to do a proper study with within the chosen network.